Hello and welcome to T Tests. So we're going to look at related and unrelated T tests today. You need to know what the T test is, both related and unrelated. You should understand what those two terms mean by now. Just to recap, most of the tests we've looked at previously have been non-parametric tests for difference. The two parametric tests for difference that we're going to look at are related and unrelated T test. So the related T test, first of all, when to use it. So when to use the test. If the hypothesis states a difference between two sets of data, if two sets of data are related, that means they're produced by repeated measures design. If the data can be treated at the interval level, and if the population is assumed to have a normal distribution and that any variance between the conditions are the same for both. Now we'll come back to what this sort of population distribution assumption means in a bit. So repeat measures. Imagine we're looking at the effect of drug A at reducing heart rate. In the case, heart rate is what we call a safe, publicly recognized scale. So two people won't look at a heart rate scale or measurement and disagree as to what the actual measurement is. But that might well be the case in, for example, a subjective measure like a rating scale of how attractive someone is. So parametric tests like the related and unrelated T really use these safe, publicly recognizable scales. So, interval measurement. Most data can be interchanged. As you know by now, interval can become ordinal or nominal. It's much harder to do it the other way around. But if we're treating data as interval, we mean that each value has an exact distance between the next. Take the everyday household ruler. The distance between 0 and 2 centimeters is the same fixed interval as the distance between 2 and 4, 4 and 6, and so forth. So in this case, a ruler is a safe measure. Some examples of other safe measures and other things would be heart rate, voltage. These are all pretty safe measurements. So you can skip this if you're not interested, but it's just worth noting one of the things that we do. Well, I say skip it, but you do need to know this assumptive normality criteria, but you don't really have to explain what it means. But essentially, a non-parametric test does not assume any particular distribution for your results. Whereas in a parametric test, we assume a normal distribution. Here's an example of a normal distribution, in this case for IQ, and we have standard deviations. So, what happens when we take samples from the same population, irrespective of the scores we produce from that population? So let's say I put all you in an experiment. Your results won't necessarily produce a normal distribution curve, but if the distribution is assumed to be normal and is normal in the population as a whole, then if I take hundreds and maybe even thousands of samples from that population and I put them all onto a scatter graph, it will produce a normal distribution curve. If you want to know more about this, central limit theorem is where you want to go for it, but as I said, you don't really need to know detail for the exam. Okay, welcome to Big School. This is, so far, most of the statistical tests we've calculated have been pretty basic. You know, compare this to chi-squared. Here's where things get a bit more complicated. The tables can be fine. Putting the data into the equation is going to be the tricky bit, and working out what to calculate first. So I'm going to take you very slowly through it, and we will work through this one together. So in this experiment, we are suggesting that more words will be recalled from deep processing compared to shallow processing. Okay, so there'll be a significant difference between the number of words processed using deep processing or recalled using deep processing compared to the number of words that used recalled using shallow processing. First thing we do is we put our sort of before and after conditions. So deep processing first, shallow processing after. They're related, the samples from the same participant. Actually, what is flawed by this study is we should have a control condition. And normally you would, but this will do for now. So the first thing we do is work out the difference, and the sign doesn't matter. So the first one, 21 minus 18 gives us 3, 18 minus 19 gives us minus 1, and so forth. Once we've calculated the difference, what we then do is square it. So 3 3s are 9, 1 squared is 1, 3 squared is 9, and so forth. You get the idea. So this is quite easy. Calculate the mean for column A and the mean for column B. I've done it here for you. And then sum this column to just add them all up and ignore the signs. Sorry, you don't ignore the signs. So add them all up, include the signs, and you'll produce 15. So 3 minus 1 is 2, plus 3 is 5, minus 4 is 1, plus 3 is 4, minus 1 is 3, plus 2 is 5, plus 4 is 9, plus 7 is 16, minus 1 is 15. So we sum that and we get 15, and then we square. You could do the sum here or you could do it here. So ultimately the sign won't matter in this column, but it does in this one. Sorry. So sum d squared equals 115. Now if we look at this equation, all the right figures are actually put in it. So we find sum d is 15, so it's 15 over the square root of n. What is n? Well, n is the number of participants in the study, in this case 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, you've worked that out from down there, so that's 10 times sum of d squared minus sum of d squared outside the brackets over n minus 1. So this is what the equation should look like, having put our figures in it. Okay, so when we're calculating this, we need to break it up, otherwise it's going to be impossible to actually fit all this into a single calculation. So if we remember our bid maths, we start with the brackets, so we're going to calculate everything inside this bracket. So we're going to do 15 times 15, and then 10 times 15, and then the sum of that minus that. And then we'll divide it by 9. So we're going to do 10 times 115, that produces 1,150. I know you can probably do some of this in your head, but I'm just going slow. So that's our first sum, we'll put that under there. 1150, we'll put it under there, change it to red, so we know we've calculated it. Then the next one is 15 times 15, which is 225. So we'll just copy that over there. That's 225. Okay, now we've got a nice simple calculation. We take 1150 and subtract from it 225, which should give us a 925. Sorry, let's do this all together. So minus 225 equals 925. Get rid of that. So we've solved this part of the equation here is 925. We then take 925, the sum of this minus this, and divide it by 9. So 925 divided by 9. Divide it by 9, and that gives us 102.78. 2.78. So we've solved this bottom half of the equation. We've done 10 times 115 minus 15 times 15 and divided it all by 9 to get 102.78. So the sum, step 1, is 102, the bit underneath here is 102.78. What we have to do now is get the square root of that and divide it by 15. So how we do that is going to be a little trickier. So let's find the square root of 102.78. So 102.78 square root gives us 10.14. Brilliant. So let's have a look at the one I produced earlier. Here I've calculated a t-value of 1.48. So there's a slight variance there, and that's likely to do with how many decimal places I rounded it to in the process. So it's one of the limitations actually of calculating it, this step-by-step approach. And if you've got a calculator that can encompass the entire equation, all the better. Generally speaking, you're not going to be asked to calculate this by hand, but you might be asked potentially to drop figures into an equation. So that's just something to think about when you're doing that. Realistically, in the scientific world, we calculate all this stuff using statistical software. So let's just go back. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 participants. So to work out our degrees of freedom, we take n minus 2. 10 minus 2 equals 8. So we're looking at the 8 degree of freedom. In this case, 0.05, meaning there's a 5% probability that our results occurred purely at chance, and that gives us the critical value of 1.860. Is our t-value greater, it's an R, so it's greater than our critical value? Is 4.8 or, 1.48 or 1.44 greater than 1.860? You can see that it is not. Therefore, we accept the null and reject the alternative hypothesis, suggesting that there is no significant difference between the number of words correctly recalled after deep processing compared to the number of words correctly recalled after shallow processing. Boom. Not a bad day's work. So that's the related T test. Remember, you can always check your answers using www.socialscistatistics.com. This is the best online stats calculator that you'll get, and it's 100% free. So by all means, check all your answers to make sure you're getting ballpark figures. Right, unrelated T test then. Let's get stuck into it. The unrelated T test makes the related T test look like the sign test. It's actually quite simple, but you have to follow along carefully and you have to practice these. So, when do we use it? When the hypothesis states a difference between two sets of data. Data are paired scores from separate groups, so independent groups. Data can be treated as interval, e.g. counting frequency with equal intervals. Populations are assumed to have normal distribution. We briefly talked about that earlier. For example, the effects of SSRIs at reducing OCD symptoms. Two groups of OCD patients, one received SSRI and the other received placebo. If the symptoms are the same, so you would select a symptom and measure its decline. It has to be a safe measurement. Females who rate higher salaries is an example that we might use in a non-parametric test. But what we could do to make it parametric is we could use their heart rate and actually physically introduce them to men with higher salaries. And that would give us an independent group study, because half would have these high, prime that they're high status males. We measure their heart rate when they meet them, and the other half would have low status males and measure their heart rate. So we're looking for safe measures. We've talked a little bit about distribution. Now it's worth talking about variance. So one of the assumptions is that any variance between sets of data is naturally occurring and will be the same in both conditions. So one way of looking at variance is if we take two sets of scores that basically range from 1 to 9 and have 5 as their mean, one set has more variance than the other. So if you look at this set here, we've got 1, 1, 3, 5, 7, 9. In this, we've got 1, 3, 5, 5, 5, 7, 9. So we've got a greater variance in this string than we do this string. The assumption then for the t-test is that any variance within a population will be equally represented, i.e. they're not all unevenly distributed, or greater variance in one, lower variance in the other. Here is a very quick example which you can have a read through to help you consolidate this. Right, the unrelated T. Look at this bad boy. State the hypothesis, and in this case we're going to have reaction times will be significantly higher in the caffeine condition than the non-caffeine condition. So we're using that safe interval measurement of reaction times, heart rate, centimeters, height, that sort of stuff. Place the raw data in the table. In this case, data is measured in reaction times. I'll show that in a minute. Calculate the value of T using this formula. Check the direction of the results, find the critical value, shows us how to find our degrees of freedom, and report the conclusions as we always do. Right, this is what our table looks like then. Let's go through and calculate it. So I've done a couple of numbers for you. What you do is you've got your reaction time for group A, in this case males, reaction time for group B, this is females, and all you have to do is square the values. So 56 is 3136, and then so forth. Down here, you sum your raw scores, you sum your squares, you sum your raw scores, you sum your squares. It's pretty straightforward. Right, here's the values filled in. Hopefully you got some of those. Just add them up. Square the sum of group A and add it here. And now we have all the data we need to put in this beautiful equation. So, first thing is we have to calculate these two variables. So SA and SB. As well as the mean for both columns as well. So let's do this. The mean for column A then is 743 divided by the number of participants, 1, 2, 3, 4, 5, 7, 8, 9, 10. Easy peasy, that gives us 74.3. 752 divided by 10 gives us 75.2. And then those two values are calculated. So you calculate your mean for column A, your mean for column B, and then we do this calculation here. To get SA, we take the sum of mean A squared, essentially, XA squared, and minus from it the sum of XA squared, and divide the whole thing by NA. So NA is the number of participants in column A. So we do this. 57145 is our sum XA squared. We minus that from 743, which is sum XA, square it and divide the whole thing by 10. That gives us 1940. Be careful how you square and divide. We do the same for our XB column. Gives us 60052 minus 752 squared divided by 10 to give us 3501. Brilliant. So that's essentially the pre-calculation for the equation. Right, now what we have to do is we have to put the values in the equation. I've done this. This is quite tricky, as the equation sees. So like we did previously, I want you to calculate all the bid mass, so all the bracket stuff first, and then we'll do the square root and division afterwards. So 10 plus 10, 10 times 10, that divided by that should solve this equation here. We put in our values here, 1940.2 plus 3501.6 divided by 10 plus 10 minus 2. So that gives us essentially this equation here. 10 plus 10 over 10 times 10, that's 20, divided by 100 gives us 0.2. And then this figure, 1940.2 plus 3501.6 divided by 18 gives us 302.22. We then times 302.22 by 0.2, and that gives us 60.44. So we solved this bottom half of the equation. The top half of the equation is fairly simple to solve. 74.3 minus 75.2 gives us minus 0.9. All we have to do now is square root and divide. So we do that. Square root of 60.44 is 7.7743316. So reasonably we can turn that into 7.77, and that's what we find. Minus 0.9 divided by 7.77 gives us 0.116. Ta-da! This gives us a t value of 0.116. It looks horrendous, but if you just take it one section at a time, you will get there. So now we need to find out if our values are significant. Unrelated T Test has an R in it, therefore we're still looking for a greater than. Our T value is 0.116. Our degrees of freedom are NA plus NB minus 2. So we have 10 in NA, 10 in NB, that gives us 20. We take 2 away from it, that gives us the degrees of freedom of 18. So we're looking at 18, we've got a one-tailed hypothesis, 0.05. We're going down, we find our critical value of 1.734. Our T then is 0.116, our critical is 1.734, T is not greater than 1.734, and therefore we accept the null hypothesis, we reject the alternative, and we say that there is no significant difference between the reaction times of males and females, which is actually what you would expect to find in such a study. No significant difference, though there may be minor differences. So that's it. Done. You've now done the two most complicated inferential statistic tests and hopefully calculated them correctly. Just a quick recap then. Test for difference, related data, interval data, normal distribution assumed. T is calculated, T must be greater or equal to critical, and degrees of freedom n minus 1. And here, test for difference, independent data, independent groups, interval data, normal distribution assumed, U calculated, and so forth. Right. Now, one thing to add to this is these tests are more powerful statistically. They are more likely to discover an actual effect. They are less likely to suffer from type 1 and type 2 errors. The only way you get better at this is by practicing, so I've got a couple that you can have a look at. I'm not going to solve this for you now, but I'm happy to work with you over lunchtime or whenever to go through it. So here is our first related T test example. Investigation into biofeedback on resting heartbeat of participants that scored high on a stress questionnaire. So in other words, this is their baseline heart rate. This is after the biofeedback training. Calculate difference, d squared, put it all in that beautiful equation. Pause it now, have a go. Alright, hopefully that worked out for you. Here's investigation into biofeedback on resting heartbeat, repeat independent group style. So this type, we take one control group, one that we train in biofeedback, and then you go through and you calculate sum of column A, square each value, sum of square sum x a squared, and then so forth, and sum these three, put them all into that big chunky equation. Well done, thanks for listening. If you have any questions, you know where I am, but thank you very much, goodbye.